We've talked about the mutual inductance between two different types of configurations of wires. And now let's consider something separate. Suppose we just have a single ring where we might have a current coming in, and that current is varying with time and coming out. Now, in this case, we know that there's a magnetic field coming from this object, and those field lines are pointing. We'll just draw them like this to give it illustration. And so inside this coil, there's a magnetic flux that's coming from the current that's running through the object itself. So what we're going to see here is this is going to be an example of self-induction. And we define it the following way. We have a flux. Magnetic flux will be proportional to the current. Why is it proportional? Because the current is generating the magnetic field. And the coefficient of proportionality is what we call L, the self-inductance. Now, first off, let's just look at the units here in SI. And we're going to calculate that this way. We have flux divided by current. Now, the simplest way to remember is that magnetic flux, so our SI units have flux is Tesla times meter squared over amps, and that's called a Henry. And that is our SI unit. But there's another way to think about this, which I'll write this way. Remember, EMF is minus change of flux. So EMF times time has the same units as flux. And EMF, that had the units of volts, and time, seconds. And so a Tesla meter squared is also a volt second. And so sometimes people write a Henry as a volt second over an amp. And that's another way to think about a Henry. So when we want to calculate self-inductance, we have to calculate the magnetic flux through our object. And we have to divide that magnetic flux by the current that's going through the object. So just like with mutual inductance, we have to, in order to actually calculate it for certain objects, we have to know what the B field is. And then we have to be able to integrate that B field over the area. Of course, a ring is kind of hard because the B field is non-uniform, but we'll look at some geometries like solenoids or toroids in which we can use Ampere's law to calculate the B field. Now, the last thing we want to point out is a crucial factor, that if I'm changing the current in this coil, then the magnetic flux through that coil is changing. And so we would generate a EMF, and that EMF is equal to minus the change of flux, and that flux is minus L di dt. Now, this type of self-electromotive force has a name. It's called back EMF. And the reason for that name is if I try to change the current in the coil, I'll generate an EMF, will try to oppose that change. And if there's a resistance in the coil, the induced current, if I try to increase the current, my induced current will flow in the opposite directions to keep it the way it was. If I try to decrease my current, then my induced current will continue to flow in the same direction to try to keep the current the same way. So it's always going opposite the way the current is changing. And that's the meaning of this minus sign, which gets this term back EMF. And this back EMF is inescapable in any type of object that you run a current through.